Welcome all of you for this course on advanced NMR technique in solid state and solution state NMR. In the last couple of classes, we were discussing various internal interaction parameters of NMR like chemical shifts and coupling constants. In the scalar couplings, we discussed lot of things. We discussed how the coupling pattern arises, what is the mechanism of coupling, and what happens to the multiplicity pattern when several spins are coupled among themselves, which they are chemically inequivalent. What happens if one spin is coupled to chemically equivalent other spins? How does the multiplicity comes? And we understood what is a triplet, quartet, how does the triplet comes, how does quartet comes, and how even though in the, for example, in the case of triplets, even though it appears as 3 lines of intensity ratio 1:2:1, we know it contains 4 peaks, because the central 2 lines will overlap. It is because if you consider the 4 possible spin orientations of 2 spins, alpha alpha and beta beta are the 2 outer peaks, and the central peak is because of alpha beta and beta alpha, both are equally probable and they are overlapped. That is one way of understanding. And actually I showed you by diagrammatically how the central peak is getting overlapped, and then we saw triplet. Similarly, we also saw quartet, and we also understood what is a pentet, what is a septet, what is a sextet, everything. All those things we understood, quite a bit we discussed. And now we were understanding the multiplicity pattern, which were called as doublet, triplet, doublet of a triplet, triplet of doublets, and various things we were trying to do. So when we were trying to understand several multiplicity pattern, we came to a point to find out when one spin is coupled to different spins which are chemically equivalent or chemically inequivalent, how does this multiplicity comes? We took an example like this, where we were seeing what happens when CH proton is coupled to CH and CH2, and I am concentrating on proton A, which is a CH proton. When it is coupled to CH and CH2, I use the condition that JAY is larger than JAX. AY means this coupling is larger than this coupling. So what is going to happen? Since I am concentrating on proton A when it is coupled to proton, single proton, CH proton, it will become a doublet. It is going to give rise to a doublet because there are only 2 possible spin states for this proton. And then each component of this doublet will be further split into triplets because of 2 equivalent protons, CH2. So the pattern what we are going to get is like this: a large doublet, and each layer of the doublet is split into triplet like this, and this large separation of this large doublet gives you a coupling between proton A and proton Y, and the separation between these 2 adjacent lines of the triplet gives you a coupling between proton A and proton X. So this is why this is the pattern we are going to expect for this type of proton when they are coupled to CH and CH2 like this. And what do you call this pattern? This pattern is called doublet of triplets. Why not triplet of doublets? That is a different question. You always start with one which is the largest coupling. Larger coupling is AY, which is this one. So this is the larger coupling which gives rise to a doublet, and then each line becomes a triplet. So this pattern is called doublet of triplets. Okay. Now the question is, what is the pattern for Y? Instead of A, if I observe Y, what is going to happen? See, now again I consider the situation, JXY is smaller than JAX. This is the chemical shift of Y. Now again there is a large doublet because of Y coupled to proton A. That coupling remains same because it is not changed. But now we also see the coupling of Y with proton X, and again it is going to be doublet of triplet. What is the difference? The change is only the separation here, that is all. Because there is a large coupling, this Y coupled to X is quite small, they are far away separated, and this is the large coupling, they are very small coupling. Similar to the pattern what you saw for proton A when you observed, it is also doublet of triplet. Only thing is the triplet separation is smaller here compared to the previous one. So now I am going to see what will happen if you observe the proton X. Proton X is the CH2 group. So far I was observing protons which are coupled to proton and then equivalent groups, CH2 group. Now I will directly observe CH2 protons. What is going to happen? What is the pattern if you observe proton X? Now proton X is going to split with split by proton A into a doublet, because this proton has only two possibilities, alpha and beta. So it is going to, and assuming this is larger than this one, what is going to happen is, first it is going to become a large doublet because of coupling between A and X. This separation gives me JAX. Now each line of this doublet is going to be split into another doublet because of this proton, and this coupling is smaller. So this is going to be large coupling, which gives rise to this one. This separation is going to give XY coupling. So this is why this pattern is called doublet of doublet. In this case, larger coupling and smaller coupling both are doublets, and it is called doublet of doublets. Now consider another example of a molecule like this. I am considering a proton A, which is highlighted in red color. Now I assume the condition AX, JAX, coupling between proton A and CH2 protons, is larger than AY coupling. Now how does the pattern come? First, A is going to be a triplet because of the CH2, and this separation gives you JAX coupling, and each line of this triplet is going to be split into a doublet because of this proton. So this is the pattern you are going to get. This doublet separation gives you JAY, and this large separation gives you JAX. And this pattern, as I said, you always start with a larger coupling. Larger coupling is a triplet and a smaller coupling is a doublet. This is called triplet of doublets. This pattern is called triplet of doublets. So you can start discussing a lot of things. What happens when a single proton is coupled to CH and CH3 now? Same logic you can extend. Now we are looking at the proton A. Again, AY is assumed to be larger than AX. When AY is larger, it has to be a doublet because there is a large coupling. A will split into a doublet because of this proton. Now each line of this doublet will split into quartet because of the CH3 group, and this coupling is much smaller. This separation, this is a AX coupling, this is AY coupling, and as I said, this being a larger coupling with a doublet, this is called doublet of quartets. We call it as doublet of quartets. Okay. Now you can also think of a situation, what happens if AX is larger than AY. If the quarter coupling between this proton A and CH3 group is larger, then this will be a quartet because of the CH3 coupling. A will be a quartet. Now what will happen? There is a smaller coupling because of this proton. As a consequence, each line of this quartet is going to become a doublet, and this doublet coupling is smaller in strength because this coupling I assume to be smaller. So what do you call this pattern? It is called quartets of doublet. Larger coupling is due to quartet and smaller coupling is due to doublet. This pattern is called quartet of doublets. Okay. So like this we can start talking lot of things, and we can think of, for example, what happens if there is a CH2 group coupled to CH3. Again you can consider varieties of possible combinations. What happens when AY is larger than AX or AX is larger than AY? The pattern changes. Now I assume that AY is larger than AX. AY is, if I consider the proton A, which is highlighted in red, because of CH2, this proton A will become a triplet. That we have been discussing all along. So this is the triplet we are going to see. Now I invoke the coupling between proton A and proton X, that is CH3 group. What will happen now? Each line of this triplet is going to become a quartet, and this quartet coupling is smaller. I have written a stick plot like this. What do you call this pattern? Triplet is larger than the quartet. The triplet coupling is larger, so we call it as triplet of quartets. Okay, this is the pattern you have to call it as triplet of quartets. Of course, we can start talking what happens if AX is larger than AY, then quartet is going to be larger if this coupling is larger, because that is a CH3 proton, 3 chemically equivalent protons. You split this proton A into a quartet, and each line of the quartet is going to be split into a triplet because of CH2 group. Now as a consequence, you are going to get quartet of triplets. Remember this nomenclature difference. Earlier it was triplet of quartets, now it is quartet of triplets because the larger coupling is quartet. This is the way you have to start naming the multiplicity pattern in NMR. When you want to analyze the spectrum, this is what you should understand. Now of course, we can think of varieties of possibilities. And these are, I am giving you common examples because you come across such type of patterns in the routine analysis of your sample. The spectra of your sample, you come across this type of pattern. So now you look at this one, the proton A, now it is coupled to two CH3 groups of different coupling strengths. What pattern we should expect? One of them is going to be a quartet because of this, but larger coupling. And now each line of this quartet has to be a further quartet because of another CH3 group. So you are going to get a pattern like this. Each line is going to be a quartet. What do you call this pattern? It is quartet of quartets. Larger coupling is also quartet, smaller coupling is also quartet. So this pattern you should call it as quartets of quartets. So this is how you start naming. Now if you look at the many of the molecule like this, you come across there may be equivalents, chemically equivalent spins may be there, chemically non-equivalent spins would be there, varieties of combinations you can think of. Consider situation we have proton A, proton M and proton X, all are chemically inequivalent. Then what is the type of pattern you are going to get? Depending upon, there are three types of coupling you can think of. Coupling between A and X, A and M and X. Depending upon which coupling is which, larger or which coupling is smaller, the patterns can change at the site of the nuclei you are observing. Now if I say the proton A experiences coupling with proton X and proton M, so it is going to be doublet of doublet. Similarly, proton X is going to experience coupling with A and coupling with M, so it is going to be doublet of doublet. Similarly, M also doublet of doublet. So this is a pattern. These are all called doublets of doublets only. Each proton will split into doublet of doublet. Now you see you can't talk for the entire spectrum. I am telling for each group is going to be doublet of doublets. And intensity pattern here is 1:1:1. Unlike in the previous example, they were chemically equivalent spins. The intensity pattern obeyed Pascal triangle, which is nothing but the coefficients of binomial expansion, which I explained yesterday. So as a result, here in the non-equivalent case, the intensity pattern will be always equal, 1:1:1:1. Okay. Now one proton is coupled to more than two different protons of or groups of protons. You can come across varieties of problem like this. Now I have one proton coupled to three different protons. I don't need to explain for you. Now with the condition I have given you, JM is larger than AX, larger than AY. Now one proton experiences coupling with three independent chemically inequivalent protons. Remember, all the three protons which are coupled to proton A here are chemically inequivalent. So what is the type of pattern we should expect? Larger coupling because of M, it is going to be a doublet. Another coupling because of X, it is going to be doublet of doublet. And then another coupling because of Y, it is going to be doublet of doublet of doublet of doublets. So it is going to be 8-line pattern. This is what we understood. When you are analyzing number of splitting patterns, how you get in the case of chemically inequivalent spins, we have worked out what is called 2 to the power of n. That you must be remembering that. So this is the pattern we are going to get for different cases. So you can also think of what happens if the situations like this, when this is coupled to CH2, CH and CH2 like this. Now it is not one or two protons, it can couple to three different protons. Remember, as I told you, one spin can experience coupling with n number of different spins as simultaneously. As a consequence, with the condition that I have adapted here, for a hypothetical molecule I have chosen, I said JM is larger. AM means M is a single proton. It has to be a doublet because this one proton, it couples this proton into a doublet. And then what will happen next? Very easy to understand. There are two equivalent CH2 groups. So each component of the doublet is going to be triplets like this. Now another this thing coupled, each will be triplet of triplets. So each component of the triplet is further split into triplets. So what is the pattern you are going to get now? This is not just doublet of doublet, it is doublet of triplet of a triplet. It is doublet of triplets of triplet. This is the pattern you are going to get. So we can see if the situation gets reversed now. If this coupling is larger than this one and then this one, now the triplet is going to be there first because of AY coupling, and then M will split each of them into a doublet because this second one is larger I have chosen. So this is going to be triplet of doublets, and then each line of his doublet is further going to be split into a triplet. So this is the pattern you are going to get. Then what do we call this pattern? Larger is triplet, then doublet, then triplet. So, this pattern is called triplet of doublet of triplets. Very easy to understand. Okay. So, you can start doing. I do not want to give many more examples. I think with the kind number of examples that I have already given to you, you must have got the hang of the type of pattern that we are expecting, how to interpret the pattern based on the chemically equivalent and inequivalent groups that are coupled to a proton that you are detecting. So, now in this case A is being detected. Again I am using the condition, this is larger than this, then now it is going to be 2 triplets and a quadruplet. So, it is first is going to be a triplet and again another triplet, and each line of the triplet is going to be a quadruplet like this. So, what you are going to get is triplet of a quadruplet. This is the pattern. So, finally, you remember one thing, this is the table which you must remember. The nomenclature of splitting patterns in NMR is like this. If it is a DD, if I say 2 doublets, it is called doublet of doublet. Larger coupling is doublet, smaller coupling is also doublet. If I consider DT, I call it a DT, doublet of triplet. What do you mean by that? Larger coupling is doublet and smaller coupling is triplet. Instead of DT, I call it TD. That means triplet of doublet, larger coupling is triplet, smaller coupling is doublet. Same thing if there are number of other protons are coupled, instead of 2, if there are 3 coupled, DDQ I call it doublet of quadruplets. Okay. First is larger coupling is doublet, second larger coupling is doublet, and then is a quadruplet. This is the way you have to understand the splitting pattern of one of the protons which you are observing when it is coupled to n number of other protons which are either chemically equivalent or chemically non-equivalent. This is the way you have to understand. So, with this multiplicity pattern we understood, I just want to tell you some idea about the strengths of the coupling. So far we said splitting is there, coupling we can measure. But what is the strength of coupling approximately? See, 1 bond coupling is always larger than 2 bond coupling, 2 bond coupling is always larger than 3 bond coupling. It is a general trend, need not always be true, many times there can be deviations, but general trend is 1 bond coupling is larger. This is hydrogen molecule, 2 protons are coupled each other, but it is chemically equivalent. In principle you should not see the coupling, because as I said there is an exception for 2ni+1 rule I said. But nevertheless there is a way we can find out by using deuterium substitution etc., which I do not want to discuss now. In the previous course this was discussed in length. Remember we have a coupling here, 1 bond coupling is very large in the case of protons. Then most of the time you come across 2 bonds and 3 bonds like this. See, 1 bond coupling in molecules like this will be 8 Hertz and 2 bond will be of the order of 10 to 12, 20 Hertz, and 3 bond is of this order in case of triplets, a triple bond. So, especially in the ethylenic substituted molecules like this, for example, if the para substitution is there, trans substitution, the trans coupling is very large compared to cis coupling, and this is quite large compared to vicinal coupling. Please remember this point, trans coupling is larger than cis coupling, this is larger than geminal coupling. This pattern you should remember, because whenever you have to analyze the proton spectrum, invariably you will come across patterns where you have to use this knowledge to analyze the spectrum. Okay. So, similarly if you look at the benzene molecule, as I told you, all the 6 protons here are chemically equivalent and each proton experiences one ortho coupling, meta coupling and para coupling. Similarly this proton experiences ortho, meta and para. So, each proton experiences 3 different types of coupling, all are chemically equivalent, but then this is magnetically equivalent with 3 different couplings. Though you will not see couplings in the spectrum, you will see only a single peak. Then how do you get the couplings? There is a way to do it, which again I do not want to discuss now, but we can know that in such aromatic systems ortho coupling is quite large of the order of 8 Hertz, meta is 1 to 2 and para is between 0 to 1 Hertz. So, this is the knowledge which I wanted to tell you, and with this I have more or less covered lot of information I have given you about the coupling patterns, spin-spin coupling. We discussed 2 important NMR interaction parameters, that is the internal interaction parameters. I discussed at stretch lot about chemical shifts. I discussed lot about coupling patterns, how we get, how do we interpret everything. We use this and analyze the pattern later. Okay, when you go to analysis of the spectra. This pattern, of course, it is, I have taken the example for the proton, but it is always need not be for proton. For any of the nuclei, if you are studying this process, this method of application is remains same. Whether you get triplet here in proton, you can also get in carbon when it is carbon is coupled to 2 equivalent protons, like that. So, triplet, multiplicity, quartet, singlet, doublet, everything, this concept remains same, and whichever the nuclei you are going to observe. So, what we will do is we will now start analyzing spectra of some different nuclei. That will give you basically an idea how to go ahead and analyze the spectrum. See, in fact, I wanted to tell you now, and before getting the spectrum, we apply radio frequency pulses at different directions and get the signal, collect and do the Fourier transformation. I wanted to talk to you about how the evolution takes place, evolution of magnetization. I wanted to talk to you about the pulse phase, receiver phase, etc. Since for the benefit of the people who have not taken the previous course, I will give the analysis of the spectrum now, and then afterwards we will talk something more about Fourier transformation, evolution of the couplings and chemical shift, phase cycling, all those things, advanced topics we will take up soon. So, now I am going to, what I am going to do is I will stop the discussion about couplings. We will straight away go to the analysis of the spectrum. We will start analysis of the 1D spectra. I have not introduced 2D, I will come to 2D later. It will take couple of more classes to introduce 2D and other things, but we will analyze the 1D spectra of some of the nuclei, right from proton NMR, which is commonly employed, carbon 13 NMR, and then various some exotic nuclei, some examples we will start, and then try to understand how to interpret the spectrum. This is very much essential when you want to apply your knowledge of NMR analysis for molecules that you have analyzed and synthesized. What do we get if you analyze different spectra? That is the first question. If I want to take the proton NMR, if I take the proton spectra, what I am going to get? See, for example, in a molecule like this, I will get information about the protons. I can make assignment of the peak and get all information about the different types of protons that are present here, different functional groups as far as the protons are concerned. If I go for carbon 13 NMR, then I know how the carbons are situated here, which carbon is bonded to which carbon, like that. If I go to nitrogen 15 NMR, for example, there is only one nitrogen, I will get information about nitrogen NMR. So, different nuclei if you study, if you take the NMR spectrum of different nuclei, then what you are going to see is different type of spectra you are going to get. The analysis gives you more information about the particular nuclei which is present in your molecule. So, I will take the analysis of first order spectra, some representative examples. First, I will tell you how we can synthesize the spectrum based on the family tree diagram, which I explained to you earlier. I will take a problem like this. Let us say there is a proton A, CH proton, single proton is attached to carbon, which is coupled to CH3 group with a coupling constant of 7 Hertz. And this is also, CH is also coupled to CH2 with a coupling constant of 5 Hertz. Now, generate the multiplicity pattern for CH proton, CH3 and CH2, all the 3 we can separate. Now, this information is sufficient. There are 3 different couplings, you must generate the multiplicity pattern. We can synthesize the spectrum theoretically. What we will do is, we will start with the multiplicity pattern for a CH proton, simple, and assume there is no coupling to anything. What is this pattern you are going to get? CH is without any coupling should be a singlet. Let us start synthesizing assuming there is no coupling. Now, I am going to bring in the coupling of CH with CH3, that is the larger coupling of 7 Hertz. First largest coupling we can think of is to couple to CH3 group. What will happen when CH3 is coupled to CH? I explained to you, CH is going to become a quartet. Clearly, it became quartet. Now, we can generate it because separation you can say it 7 Hertz because that is the coupling information given to you. Use this 2ni+1 rule and generate the multiplicity, you get a quartet. Further, this is also coupled to CH2. That coupling is 5 Hertz I said. So, each line of the quartet become a triplet. So, what do you call this pattern? Quartet of triplets. So, you can generate, synthesize the spectrum of this molecule. This is what we understood. So, this is a typical example we saw for this molecule. You can synthesize for the CH proton. Now I will take what happens if I take the CH3 proton. I am observing CH3. Again CH3 without coupling is a singlet. Now with this coupling to CH, it is going to be a doublet. Remember, when I was observing CH, it was a quartet, but now I am observing CH3, so it is going to be a doublet. And this doublet is further split into CH2. Each of them is going to be a triplet pattern. So it means you are going to get doublet of triplet for CH3. Remember, for CH you got different pattern. For the CH3 you got doublet of triplets. So this way you can start analyzing this. Now we will try to synthesize the spectrum of analyze the spectrum, synthesize how we get a spectrum for a simple molecule CH2D2. It is a methane, the deuterium substituted, 2 protons are replaced by deuterium. Now analyze the 1s spectrum for this. What is the type of spectrum you are going to get for this? There are 3 types of NMR active nuclei present in this molecule. One is carbon 13, that is spin half, proton spin half, deuterium spin 1. There are 3 nuclei. When there are 3 nuclei, you can think of 3 different types of coupling. There can be a coupling between C and H, there can be a coupling between H and D, there can be a coupling between C and D also. That is also possible. So all the 3 types of couplings you can think of. But I will give you a condition. Carbon 13 is in natural abundance. Natural abundance means its abundance is only 1%. So generally when it is 1% abundant, we see small intensity peaks on either side. We call them as satellites. This we discuss again in the earlier course. So remember, when I consider carbon 13 the natural abundance, you should get only satellites. Now let us see analyze the 1s spectrum of CH2D2. What is going to happen? If I look at the carbon 13 atoms which are not abundant, we will ignore it because they are satellites. Right now we do not worry about it. But then it will couple only to deuterium. Then what is the pattern you expect? The pattern you expect, it is simply put the 2Na plus 1, deuterium spin is 1, there are 2 deuteriums which are coupled to proton. So 2 into 2 into 1 plus 1, so you are going to get 5 length pattern and the intensity is 1:2:3:1. Very simple. If you take this molecule, take the proton spectrum, you are going to get a pentate of intensity 1, 2, 3, 2, 1. Now what happens if I get the carbon 13 spectrum? But remember, carbon 13 when I am observing proton is a satellite, but when I am directly detecting carbon 13, I do not worry about satellites because then these 2 are abundant. So they will directly couple to that and I am directly detecting carbon 13. Now what will happen to that spectrum? Carbon 13 is split into triplet because of CH2. What is the intensity pattern? See, carbon coupled to 2 chemically equivalent protons, intensity is 1:2:1. Now each line of this multiplied is split by the presence of 2 deuterium atoms, spin is 1. Use this 2Na plus 1 rule again and now you are going to get 5 lines. So each line of the triplet of carbon 13 is going to be a pentate. So we get triplet with each line is being pentate of the pattern, intensity pattern 1, 2, 3, 2, 1. So this is how we get each line is going to be a pentate and then each line of the triplet is going to be a pentate like this. Now what happens if I see the deuterium now? That is another possibility. I can also see it. I saw carbon 13, I saw proton, I agree. What about deuterium then? See, deuterium is split into a triplet because of CH2, 2 protons, equivalent protons. True. Then will it not couple to carbon 13? Yes, it does couple to carbon 13, but carbon 13 appear as satellites. Since I said it is a natural abundance, right now we do not worry about it. So it is small intensity peaks. If you ignore, there is a coupling, but still if you ignore, for the deuterium spectrum, you are going to get a triplet of 1 to 1. Supposing you also look at the carbon 13 satellites also, then either side of the triplet, you are going to get 3 more lines, which is 3 satellite lines, which are split into again triplet because of this. So this is how you understand the spectrum of it. So now I think the time is up now. What I am going to do is, I will stop now. What we understood today is, I completely told you a lot of information about the coupling, multiplicity pattern, strength of coupling, how do you generate different types of coupling, How do you, what is the nomenclature for the pattern? Whether it's doublet, triplet, triplet of doublet, doublet of triplet, quartet of triplet, all those things we understood. Depending upon the strength of the coupling, we can do. It is applicable to every type of nuclei, not necessarily proton. And then we synthesize the spectrum. We know how to synthesize the spectrum based on the family tree approach, whether one proton is coupled to chemically inequivalent proton or chemically equivalent proton. Depending on that, we can generate the multiplicity pattern. So, we understood simple molecule like CD2, CH2D2 if you take, how the proton spectrum comes, how the deuterium spectrum comes, how the carbon spectrum comes when it is coupled to spin half nuclei and also spin 1 nuclei. So, these are all interesting things which synthesize the spectrum to understand by using the knowledge of multiplicity pattern. That is why I said this is very much useful in the analysis of the spectrum. So, now what we will do is, we will stop now, we will come back and then continue with analysis of few more spectra of protons and then other nuclei. I will stop here. Thank you.